Okay, so first I'm going to talk about the electric field, and then I'm going to transition over to magnetic fields. So, a field, a vector field, is basically a vector assigned to every single point in space. If you have a charge, for example a positive charge, it will create field lines that look like this. They, these arrows decrease in strength like asymptotically, but they go all the way out to infinity. So something like this. Uh, if you have a charge, another charge here, like for example at this point, um, the force that acts on this charge is completely, the electric force is completely determined by the vector of the electric field that it's at. So this arrow, let's say has a strength of 5. The formula says that force equals Q times E. These are vectors. So the force will be in the direction of the electric field vector. So this vector, it's pointing out this way. So the force will be pointing towards this way. And the magnitude will be taking the charge and multiplying it by the strength of the electric field at that point. You can have like many different charges, positive and negative, scattered in different locations, and it could create like a random field that looks something like this with no particular pattern. This would still apply. If you take any charge, you put it in here, for example, at this point. In order to calculate the force, it would just be taking the magnitude of the charge, multiplying it by the magnitude of the electric field. So the length of this vector, basically, and the direction will be in the same direction as the electric field. This is what happens with magnets as well. Okay, so like this charge I drew before is a monopole because it only has a um, positive charge and no negative charge. So it creates field lines that go outwards, right? But magnets are always dipoles. It always has a north and a south. There are no magnetic monopoles. That violates Maxwell's second law. So it creates field lines like this. There are electric dipoles as well. Something like this. However, the field lines of an electric dipole look like this. So these go this way, and these go outwards from the positive, and get sort of sucked in by the negative end here. So these field lines are going this way, but then it changes direction here, and it goes this way, like goes downwards. But for a magnet, if I make this sort of like transparent, these continue all the way up, and they don't stop. They're all loops. They all go in the same direction. So that's one of the big differences. If you have a magnet in a magnetic field, so for example, north-south, this, it will align itself to the magnetic field. It'll experience a force, right? This north pole here will be repelled by this north pole because, similar to electric fields, like the electric force, the magnetic force will um, repel like poles, like charges. So this will cause it to align with the magnetic field this way, because this north is attracted to the south pole, and this south is attracted to this north pole. If we zoom in further, so like at this particular spot, these lines are almost parallel. And the reason why this happens, so like for example, if the magnet was originally like this north will be will experience a force this way because it's in the same direction as the field lines. Remember, but the south pole will be this way because it's in the opposite direction of the field lines because south is like the opposite sort of charge of north, which flips the vector direction around. So yeah, this sort of force configuration creates a torque, which causes it to rotate until it's like this, and then it's in equilibrium, so it doesn't rotate anymore. So that's why magnets align with itself with the magnetic field. Okay, but what is magnetism? Where does it come from? Let's say you have a wire and you have a current going this way. Um, Oersted's discovery states that a current, any moving charge, causes a magnetic field. And so this is like the most basic way of creating a magnetic field. Hold out your right hand, make a thumbs up sort of thing with the right hand. If you align your thumb with the direction of the current with I, all your other fingers curl in the direction that the magnetic field would. So clockwise in this case. So if you have your thumb like this, all your fingers would go like this sort of in this direction, right? And that's how you'll figure out which direction it would go in. But you might be thinking permanent magnets, well, like bar magnets, they don't have any sort of um, current in them. So why do they have a magnetic field? It's because in the atomic level, the electrons themselves are spinning. Right? They have this quantum spin, which I will not get into, but it sort of acts like a current, which creates a magnetic field. Some elements have the property that not all of the electrons magnetic fields cancel out because remember the law that we learned in chemistry that states like these must have opposite spins, the electrons in the same thing, and they usually cancel each other out. But some elements have electrons left over that don't get canceled out, which makes the atom itself magnetic. And if enough of these atoms align with each other and don't cancel each other out, that makes the entire the entire like object magnetic. So that's where permanent magnets come from. Okay, if I were to take this wire and I make it into a loop. Okay, let me draw it better. Or 3D. Okay. And let's say the current is going counterclockwise. According to the first right hand rule, the magnetic field would loop around it in this sort of fashion. Right. You align your thumb like this, your fingers curl this way. So something like this. Okay, so this creates a thing where it's where like the top side of this loop has like a magnetic field coming out of it, and then all the other field lines end up at the bottom, right? And then they curl right back up. This should be reminiscent of a bar magnet, which does the same sort of thing. So, if you have a loop, which is called a solenoid, it creates like an electromagnet type of thing, which is similar to a bar magnet. And you can increase this effect if you have a bunch of loops together, or in other words, if you have a coil. All of these will have like tiny loops and they add together, and then they make like a big magnetic field. The strength of this magnetic field can be increased if you put a paramagnetic object or a ferromagnetic object inside of the solenoid. Okay, so we talked about the the electric force, but where does the magnetic force come from? Well, this was first discovered by someone who forgot the name, but someone took two wires and then they passed a current between the both of them, and they went in the same direction. And this created a force which caused the wire to go like this. They were attracted towards each other. Uh, so the conclusion that they drew was that if you have a moving charge in the magnetic field, then a force will be exerted on the charge, right? Because remember, this wire creates a magnetic field this direction, so and it affects the wire on the left. This also creates a force and affects the wire on the right. Yeah, and because these wires were in the other wire's magnetic field, it experienced the force, and they concluded that it was due to the moving charges inside, because once they turned the current off, there was no more force. So the magnetic force must have been due to the moving charges inside of the wire. So this is the formula for the magnetic force. Okay, this is a cross product, it's not just simple multiplication. So what does it mean to have a cross product? Well, if you have a vector A cross with a vector B, and for example, let's say the vectors are like this. Okay, they're perpendicular. The way it works is, okay, first you would need to, okay, let's say it makes the vector C. Which direction would the vector C be pointing? This is the second right hand rule. You take your thumb, your second finger, and your third finger, and you make them all perpendicular to each other. So like, your second finger is like here, your third finger is like here, and your thumb is pointing up, sort of like this. And the rule is, your second finger crossed with the third finger makes a vector in the direction of your thumb. So since we're doing A cross B, we would align our second finger in the direction of A, our third finger in the direction of B, right? And then our conclusion would be that, because this corresponds with this corresponds with this. But if you rotate this hand to match this configuration, your thumb will be pointing upwards. So therefore, the vector C will be pointing upwards. And of course, the magnitude of C would just be equal to, so magnitude of C would be equal to the products of the magnitudes of the individual vectors. So it's like normal multiplication with the magnitudes, but the direction will be changed. So this is perpendicular to all three. All three of these vectors are perpendicular to each other. What if A and B weren't perpendicular to begin with? So let's say A is like this and B is like this. C would still be in the same direction, right? And I'm not going to get into why, but the magnitude of C will be different. Magnitude of C would instead be A, B, sine theta, where theta is the angle between them. Here, theta was 90. So this is still technically sine theta because it's still a cross product, but since theta was 90 in this case, sine theta became 1, and you can ignore it because sine of 90 is 1. So that's why in perpendicular cases, C would just be equal to the product of the two vectors, whereas in any other case, you would have to multiply by the sine of theta. Okay, so back to F equals QV cross B. Let's say you have a magnetic field running across the screen like this, going upwards. So that's our B magnetic field. Okay, by the way, B is measured in. Okay, so B is to magnetic force as E is to electric force. E is the electric field, B is the magnetic field. It's also called the magnetic flux density, which I will get to later. Why it's called magnetic flux density. So this is magnetic force, magnetic field. Magnetic field or magnetic flux density. It's measured in Teslas. So the SI unit for this is Teslas. And this is basically how strong the field is, or how long the arrows are. Let's say you have a charge with a charge of Q moving along with a V, a velocity this way. V stands for velocity. So yeah, uh, if you look back at the formula, if there's no V, this entire thing would be zero, and there's no magnetic force. So you need to have a moving charge to have a force. That's why in this experiment earlier, when there was no current, there was no attraction between these two wires. So you would do the right hand rule. Okay, so you would point your second finger to the right. Your third finger would point upwards, which causes your thumb to point in the direction of like it points out of the screen. So if you have, your second finger goes to the right, third finger goes upwards, your thumb will point out of the screen if you rotated your hand to match the configuration. So this would be the direction of F, and the magnitude would be just Q times magnitude of V times the magnitude of B and sine theta. But theta here, right, is perpendicular, so it's 90 degrees because B and V are perpendicular like this. So this will just be 1, so we can ignore that. Okay, so now we have the magnetic force out of the way. We can go and explain why these wires had an attraction the way they did. Oh yeah, another thing to note is that current is the direction of the flow of positive charge, right? And we know that electrons flow in a wire, not positive charge, not protons. So this is because people back then thought that protons, like positive charge, was the thing that flowed, not electrons. So that's why it got messed up, and we kept the convention from back then because nobody changed it. So despite electrons being the thing that actually flows, we define current as the flow of positive charge. So the effect that this has is that, for example, if you have a wire and electrons are flowing this way, we'd say current is flowing this way, right? So negative charge flowing to the right is mathematically identical to saying that there is positive charge flowing to the left. So it's like if you have a battery, like this, right? Positives here, negatives here. You say the current flows this way, but in reality, electrons are flowing from negative to positive. So this is the flow of electrons. But we say current is flowing this way because it's the flow of positive charge. The math works out the same, so that's why nobody changed it, but in reality, the electrons are the things that are flowing. Okay, so here. Okay, so let's say electrons are flowing downwards, which means the current is going upwards. Right, according to the right-hand rule, it creates a magnetic field. I'm just going to take one cross-section of the magnetic field created by the right wire, okay, and see what effect it produces on the left wire. Okay, so zooming in on this very specific point, okay, the velocity of positive charge is upwards. Technically it's electrons going downwards, but we can say it's like positive charge going upwards. That's our V. If you look closely here, B would be going out of the screen. Like this field would go out of the screen, go back into the screen here, come back and come out of the screen here. So B is sort of like, picture this as going out of the screen. And I said earlier that this current will be, this wire will be attracted to the right. So there will be a force here. And this matches with our right hand rule, right? Second finger goes up, third finger goes out of the screen. This makes the thumb go to the right. So that's why this current carrying a wire would be pulled in the right direction. If you do the same thing with the right wire, like if you say, oh, this wire would create a magnetic field like this. Sorry, this way. Right. The magnetic field goes into the wire. Velocity goes upwards. So instead, B would go into the screen. This would flip F around, because if you put your second finger pointing up, your third finger pointing into the screen, that makes F go to the left. So yeah, that's why they will be attracted towards each other. Like this. Oh yeah, one more thing I want to talk about is, okay, B here is going into the screen. I don't have to represent it this way. I can represent it as this. Okay? Imagine a vector looking like this. Vector arrow looking like this. In order to represent this thing coming out of the screen, it would look like the tip of the arrow and the circle of the arrow, like this. If it's going into the screen, you would see the tail in the circle. So if it's going into the screen, it would look like this. If it's coming out of the screen, it would look like this. So that's also how people would represent it in a different way. Okay, what next? Alright, yeah, okay, so let's go back to the solenoid. So let's say I have many loops. Okay, each of these loops creates a magnetic field, a B. And then since I have many of these, it would be like whatever B the first loop creates multiplied by the number of loops there are. That would be like the total B, the total magnetic field that it creates. So we know that a current creates a magnetic field. So something electric would create something magnetic. But that would lead to the natural conclusion that if you have something magnetic, that would also cause something electric to happen. And so that's Faraday's discovery, or Maxwell's third law. Okay, its complete form is this, but don't worry about it yet. 5T E. Okay, so what this means is, well, not really, but this is like calculus notation, but you could understand it as change of this phi means magnetic flux. So change in magnetic flux divided by the change in time. Let's interpret this step by step. Okay, so this negative sign is just a directional thing, so don't worry about it yet. It's just a directional thing. So basically, this epsilon here means electromotive force, so basically voltage. So what this law is saying is change in magnetic flux over time. So how fast this magnetic flux is changing creates a voltage. So magnetic stuff makes electric stuff happen. And a negative sign to change the direction that it's actually going in. Okay, so what I usually do is I ignore the negative sign. And I figure out the direction of V later, afterwards. I'll show you what I mean. But first, in order to understand this, you need to understand what magnetic flux means. Let's say I have a sheet of paper, and there's wind blowing from the bottom up, right? So there's a bunch of wind going into the paper. How fast the wind is going is like analogous to what B is. So B it's sort of like the wind speed, the length of these arrows. So it's sort of like wind speed. The area of this paper is A, so A is area. Okay, would it make sense if I told you that the more area that this paper has, like the more uh wind that it catches, right? And the more force that it has, that it will experience from the wind. So, okay, so this is what people define as magnetic flux. But if you don't know what this means, just interpret it as B, the strength of the magnetic field, times the area that the arrows are going through is the magnetic flux. So if you have, and this is so analogous to a paper in the wind and how much force it receives. So the flux is sort of like how much force the paper receives from wind. B is the strength of the field, and it is analogous to the wind speed. Okay, so before I told you that B is magnetic flux density, right? Density in this case would be like stuff divided by area, right? Um, mass density is mass divided by volume. Mass density in a sheet of paper would be mass divided by area. Um, so if you want to find the density of something, you would divide by area, volume, or length, depending on what dimension it is. Since it's a sheet of paper, you divide by area. If you divide by area, so this is the divide by area, divide by area, you get B back. So B equals flux density. So that's why people call it magnetic flux density. Okay, so what if the wind weren't blowing perfectly perpendicular to the paper? What if instead it's blowing at an angle? Wait, let me draw this vertically instead. So you have a sheet of paper, and you have wind blowing this way. What if the paper were instead tilted 90 degrees so that the wind doesn't blow it at all? It's in the same direction as the wind. The paper wouldn't receive any force because imagine that it's infinitely thin. Uh, this wind wouldn't hit any sides of the paper, and so there would be no force exerted on the paper. So that's why this is a dot product. What a dot product means is, I'm not gonna get into it, but this dot here means just take B times A times the cosine of theta. Here the theta was 90 degrees. I'm sorry, the theta was 0 degrees, and the cosine of 0 is 1. So let me show you what theta is. So if you draw a line perpendicular to the surface of the paper, this like a normal vector, then the angle between this vector and this vector is 0 because it's parallel. Whereas here before, it's blowing against the side of the paper. Normal vector would be pointing straight out here like this way. It's perpendicular to the surface, and it's perpendicular to this vector. So cosine would be 90. Therefore, in this case, B dot A cosine 90 would be 0 because cosine of 90 is 0. Okay, if you didn't understand the cosine part, it's fine, because I don't think Volk is gonna go over it. But just know that this is how it works. In the law, okay, so let's go back to Faraday's law. Negative d phi, change it, phi, magnetic flux. So this is dt. Can rewrite this as negative change in B times A over change in time equals electromotive force. So let's say, so what it's saying is, if you have a loop of wire, and there's magnetic field going through it, this wire would have some magnetic flux, right? Because there is a B, there's a magnetic field going through its area, A. And the change of this B dot A over time would be the voltage induced here, and the voltage would create a current. So basically, uh, if you have a changing magnetic field going through a wire loop, then it'll create a voltage. If it's not changing, then B dot A over time would be 0 because there's no change over time. And you can increase this. Okay, let me change this a bit. If I do times n, then that means if you have n is the number of loops this has. Because if you have a bunch of loops, then this will have a bigger effect, right? Because the magnetic field is going through many of these loops, so it's going through n multiples of this area. So it's gonna have a bigger flux. So change over time will be bigger. So that's how you might also see it be written. So if you see n in the formula, this means number of loops. But here I'm just going to talk about a single loop. Okay, so remember how I told you to ignore the negative sign? This is why. So let's say you have B equals 5 Teslas. So all these arrows have a strength of 5 Teslas. Let's say this area is 10. And after 2 seconds, let's say the magnetic field rotated so that, let's say there's a magnet down here, north, south. So it creates this magnetic field, and it goes like this, right? And afterwards, I rotate it so that the magnet is now here. So it's now going perpendicular to the normal vector of the coil, but it's going parallel to the coil itself. It doesn't have any flux. So it loops back around like this, right? But I'm just going to draw this section of it. So here the flux would be 50. 5 times 10 is 50. Here the flux would be 0. So this is at t equals 0, time equals 0. Time equals 2 seconds. And so in this time interval, what is the voltage created in this loop? Well, because you have a changing magnetic flux, there will be a voltage. So over a span of 2 seconds, that's the delta t, the change in flux went from 50 down to 0. So the change would be 50. So basically, the electromotive force, the voltage, would be 25 volts inside this wire if the situation occurred. But however, you don't know what direction it is. You don't know if the voltage creates a current this way or if it creates a current this way. And to figure out the direction, you could either use the negative sign and do vector stuff, or you could also use the easy way called Lenz's law. So what Lenz's law is saying is the induced current. So basically, the current produced when there's a changing flux in a coil of wire, the induced current will produce its own magnetic field that opposes the change in the magnetic field. So in other words, let's go back to this example. So here there was a magnetic field going up, and here there's no magnetic field anymore, no magnetic flux. So flux going up, no more flux. Therefore, you can think of this as like up flux. I'm gonna call this like up flux, and then no flux. So you see that flux has gone down, sort of. Like if we continue this pattern, there will be some down flux, right? There will be some arrows going downwards. This magnet will rotate all the way up here, and there will be arrows pointing downwards. So it was here at first, rotated here, and now it's and if you continue the pattern, there'll be arrows pointing down. So here the flux is decreasing. So the new magnetic field, according to Lenz's law, would oppose this change. It would try to create more upflux to counter this change. So, in other words, whatever the direction of the current is, it would create a magnetic field like this. The magnetic field will go upwards. And according to right hand rule, let me take a sort of cross section. So this is the new magnetic field. So I'll call it B2. This is the original B1. This new B2 would be smaller, right? But it'd be smaller, so it wouldn't completely counteract B1. But it would oppose the change in B1 a bit. This new B2, if the current is going, if the magnetic field is going this way, according to the first right hand rule, the current must be traveling in this direction. So the conclusion that I can draw is the new electromotive force, it creates a current that goes counterclockwise. Alright, let's do one more example because this can be confusing. Okay, let's say there is a piece of wire like this, and this extends infinitely, right? This is a piece of wire. And there are a bunch of magnetic field arrows going upwards across this entire thing. Like, pretend there's a big bar magnet down there with the north face here. This goes infinitely as well, and then has a south here. So these arrows will continue and continue and continue like this. So pretend there's a magnet down there that causes all these field arrows going up and through the wires. I'm just gonna take out some of these arrows. And let's say you have a metal rod like this, right? And you move this to the right. So here, the loop is like this. It does a loop like this. After you move it to the right a bit, after you move this rod to the right, so the rod is here now. The loop is bigger now. So there's a bigger loop, bigger area. And the rate that this area increases, let's say this area increases by 5 meters squared per second. So every second it gains an extra 5 meters squared, 5 square meters. And all these arrows have a strength of 7 Teslas. Oh, sorry, this should be A over T because it's area over time, change in area over time. So this is B. Let me write the formula again. Formula states that change in B times A over T is this. And the question is, which direction would the induced current be? So it's either going to be, since the loop is like this, it's either going to be this way, a counterclockwise current, or it could be a clockwise current this way. For I. Okay, so first let's figure out the magnitude of this. So let's figure out the voltage. So this would be, ignore the negative sign, remember? So 7 Teslas times, we don't know A, but we do know A over T. Change in area over time. That's 5. So 35, oh yeah, the SI unit for magnetic flux is Webers. So like this, abbreviated as WB. Webers per second, because time down here, top here is flux. Okay, this equals voltage, right? So voltage is 35 volts. And what's the direction of the current that this 35 volts creates? We can find the magnitude of the current if we know the resistance, but let's not do that. Let's just find the direction. So here, okay, so let me draw this. Let's say the metal rod is here at the beginning. It has a little bit of flux going upwards, but further along in time, it has a bunch of flux going upwards. So to oppose this change, it would have to create some flux downwards. So the new current that it creates would have a flux going downwards. So you have a loop that creates some flux downwards. Which direction would this current be? Well, a downwards. Okay, so you pick one point here. Downwards flux could be represented like this. Magnetic field going this way. What kind of current would produce a magnetic field going this way? According to the right-hand rule, it would be a current going counterclockwise. So the answer would be a counterclockwise current. One application of this Faraday's law is electric generators. So what they have is they don't have one loop, but they have multiple loops to increase the d phi dt. Sorry, change in flux, change in time. To increase this, you can have, remember, d phi dt delta phi is this. To increase the top, you can also add more loops, which is the n, but here I'm just going to represent it as a single loop. But in practice, they usually have many loops. And let's say that you have a magnet, circular magnet. So let me just take. So this is the loop. This is the output of the loop. Okay. So we have a magnet with north here, south here. So magnetic fields go this way. Of course, there'll be two magnets, but yeah. I'm not gonna draw the other pole. So think of it as north making fields getting sucked in by the south pole. This creates a downward flux. When you rotate this coil, this changes the flux, right? Because you're changing the angle that this makes with the magnetic fields. That creates a change in flux over time, and this changing flux creates a voltage. And the output of this is actually alternating current. So that's how alternating current generators work. And I think that's it. So like,